When temperatures and precipitation rise, the risk of diseases like malaria and cholera increases. AI and Earth observation are excellent tools for staying one step ahead. I want to walk you through a forward-thinking process, using machine learning and Earth observation data to predict disease outbreaks. Imagine anticipating where and when diseases like malaria or cholera might spread, just by predicting the weather, and doing this globally. This capability has enormous potential to save lives and improve resource allocation during public health crises. I will walk you through a simplified process outlining the key steps. Whether you're a public health professional, a data scientist, or just someone curious about how technology can make a difference, I think you'll find this interesting. So let's dive in. The first step is collecting correct and complete data, which is crucial for accurate predictions. We start with past disease outbreak data for disease records, such as weekly case counts for diseases like malaria, and it can be recorded at the district level. These records form the backbone of our analysis. Earth observation data from satellites provides critical information like land cover, temperature, humidity, precipitation. These environmental factors often influence how diseases spread. Demographic and socioeconomic data from sources like World Pop and the Relative Wealth Index provide population density and economic indicators, which are key factors of disease transmission. GIS data includes water bodies, transportation networks, and healthcare facilities, features that either contribute to or help mitigate the spread of disease. These datasets provide a comprehensive view of the factors influencing disease outbreaks. Once the data is collected, we must prepare it for machine learning. This involves several steps. Standardizing formats ensures all datasets are in the same structure and aligned spatially and temporally. Zonal statistics are used for district-level analysis, where we calculate averages or totals like mean temperature or total population for each district. This helps us integrate environmental and demographic data. Spatial analytics are techniques like clustering and buffer analysis that help us identify patterns, such as the number of people living near a river in a disease-prone area. Cleaning the data removes duplicates, handles missing values, and normalizes them. For example, scaling values like temperature and population density to a consistent range makes the model training process smoother. These steps transform raw data into a structured format, often resembling a large table with rows representing districts and columns representing features like population, precipitation, and past disease cases. Now comes the fun part, training the machine learning model. First, we decide on the type of problem. Regression models predict the exact number of cases, and classification models categorize districts as low, medium, or high risk. AutoML libraries include tools like AutoGluon to help automate model selection, hyperparameter tuning, and preprocessing. This saves us time and ensures we get the best model for our data. AutoGluon has been the best option for me in the past, but I've also used other libraries like AutoSKLearn and AutoKeras. It's important to know that machine learning doesn't just predict outcomes. It also highlights the most critical factors. For example, it might reveal that proximity to water bodies and precipitation are the strongest predictors of cholera outbreaks. After training the model, we must evaluate its performance to ensure accuracy, reliability, and generalizability. For regression problems, we use metrics like root mean squared error, or RMSE, to measure how closely predictions match the actual values. For classification problems, we use metrics like the F1 score, which balances precision and recall to effectively handle both classes, high and low cases, for instance. A proper train-test split of the data ensures the model isn't overfitting and performs well on new data. Evaluation helps us understand how well the model works and through the errors highlights areas for improvement, like adding more data or refining features. Feature importance analysis identifies which features had the most impact on predictions. SHAP values are another method with a similar goal. These can be used to identify critical factors for disease spread, such as temperature or population near water. With this new knowledge, we can return to the data collection step, add new variables, and retrain the model to improve its accuracy. This iterative process helps us build models that are not only accurate, but also insightful and generalizable, providing actionable information for public health decisions. Using machine learning with Earth observation data offers several key benefits. First, this proactive approach to public health allows us to anticipate and prepare in advance instead of reacting to outbreaks. Second, decision makers can target interventions for efficient resource allocation, like vaccination or sanitation efforts to high-risk areas. Third, this approach works across diseases and regions, making it scalable and adaptable to public health challenges. Fourth, with a trained model, we can run simulations to explore scenarios, such as how 1 degree temperature increase might affect malaria cases, or how improved water sanitation could reduce cholera outbreaks. Other potential applications of this approach, combining Earth observation and demographic data with machine learning, can be applied to various challenges far beyond disease prediction. For example, it can help mitigate urban heat islands by identifying vulnerable neighborhoods using temperature and land cover data, guiding cooling initiatives like tree planting. It can also improve food security by predicting crop yields based on vegetation indices, precipitation, and soil moisture, allowing for better resource allocation and early warnings of food shortages. Other applications include disaster preparedness, where satellite data helps map floodplains or wildfire-prone areas. Demographic data identifies at-risk populations, improving evacuation and aid strategies. Satellite data can also monitor air pollution and predict health risks, enabling targeted interventions to protect vulnerable groups. Finally, this process can guide equitable infrastructure development by analyzing access to roads, schools, and healthcare facilities, ensuring underserved areas receive critical investments. And there you have it, a step-by-step look at how machine learning and Earth observation data can be used to predict and prevent disease outbreaks. This process combines advanced technology with public health insights, creating tools to make a real difference in people's lives. I'd love to hear if this inspires you, or if you'd like to collaborate on similar projects. Together, we can push the boundaries of what's possible and work toward a healthier, more resilient world. Thanks for watching, and I look forward to seeing you in future video. In a future video, I'll provide even more technical details on various ways to set up a machine learning problem than what I described here, what worked and what didn't work for me in predicting disease outbreaks, and potential extensions of this research. So, see you then.